The chairman says that we have to start now. And the first speaker of this session is Scott McIntosh on the remarkably abrupt transition between solar cycles. Go for it.
25 and 5, I believe, Steve. That would be 35 and 15. All right. My boss, Cheryl, asked me to give out some call-outs that we need to have, or if you're willing to share the PDF of your presentation, please either email it to her or find the link to the Google Drive. Big Brother's watching me. You'll find the link for the Google Drive on the meeting agenda. So I just wanted to start by kind of doubling down on Bill's beautiful talk this morning and saying that my first interactions with Professor Thompson, who was Dr. Thompson at the time, were rotated around my early graduate student career doing inverse problems. And I rattled off a few questions. While I wasn't working in helioseismology, I was working on coronal diagnostics, and they're very similar inverse methodologies that could be applied. And so I was very curious about the Backus-Gilbert techniques in geology and wanted to get into understanding OLA techniques through MOLA and SOLA. And so I sent Michael an email as a newbie graduate student expecting to get absolutely flamed in response. I got nothing of the kind, and I got tremendous help from both him and Frank to help me get through the initial teething of that. So my interaction goes back 20-something years with Michael, although I didn't get to work directly with him until he came here in 2010. And so also I want to make sure that I carry the best wishes and regards of the organization to you all. That's all of NCAR and also UCAR. Michael was dearly loved in this place, and we still feel his loss on a daily basis. I will say probably none more than me, because I'm the person that stepped immediately into his shoes to try and cover some of the incredible workload that he was taking. In fact, just to pay credit to Michael, it's basically taken two of us to get through a similar amount of work that Michael got through, just to give you an idea of scope. So either we're profoundly lazy or stupid, right? Maybe not either, but it shows you the incredible dedication that Michael had to NCAR and UCAR, and poor Michael had to make some very hard choices in his life as HAO director that most of you probably know about. Those didn't sit well with him. And I think Steve and I, having been directly in Michael's circle, know a lot about what he went through. And I can tell you that I greatly valued seeing the deliberation and the careful understanding of data that went into making those decisions, which we all kind of have to do as leaders sometime. We have to make things that really don't sit well, but make to some degree logical sense. And so I owe a lot to Michael for my own style of leadership and willingness to team with people, because I think that was one thing that he demonstrated greatly, was his ability to develop teams and work in teams with people across all aspects, as Jorn also indicated this morning. So thank you all for coming, and I do appreciate your time, and I'm sure Michael would be sitting with a wry smile, kind of sniggering at us all, lamenting him, and but I think you'd also get off on the science, because ultimately he and I were planning this workshop a year ago, almost exactly. Didn't quite pan out the way we wanted it to work out, but I'm sure that by the end of the 2.5 days or 3 days of conversation, we may make significant progress in helioseismology and try to figure out the path forward. So I will digress a little bit, but also you'll see elements of this work that resonate with Rachel's presentation and some of the other things that you saw. And I'll pay homage to the egregious use of James Cameron's characters without actually acknowledging them. And so I'm going to talk about how solar cycles end. And many of you may think that it's the sun's a very diffusive thing, with the exception of maybe the corona with flares and such. But turnover time is very, very slow. I beg to differ, and I'm going to try and show you that that's not the case. In fact, it's remarkably sharp in response. So since I've been doing this work, almost by accident, starting in 2011, I had been talking with Michael about a lot of these things, and one of the things that came up was this getting around this myth that the very sensitive coral-like object that is the corona responds very sensitively to changes in the magnetic field underlying it. And so you could detect things that were potentially deep-rooted in the interior through their manifestation in the corona. And an old wise mentor of mine got me tracking things in 2002. Things that he had been capturing as part of his research career. But I don't know, I'll get into that a little bit later, but I owe also a lot to Joe Gurman for getting me started down this path and what I found by accident on the way. So bear in mind that the corona can reflect things in a very sensitive way that you may not have originally anticipated. And so what we got to tracking were these small ubiquitous features in the corona called coronal bright points. Now, being a solar physicist, the glossary of terminology is usually smacking you in the face. What are they? They are small bright points in the corona. Nothing more, nothing less. And yes, it took several years to figure out that there was a small magnetic dipole underlying said things. Shock horror, the progress of solar physics. But what we noticed very abruptly, and I can remember busting into Michael's office and saying, this is odd, because I'd always been under the impression that coronal bright points belong to every dipole in the photosphere. So if you can think of the photospheric magnetic field distribution, there's dipoles all over the place. Hi, Stuart. Good to see you. But that's not the case. In fact, when you studied these things in great detail, or any kind of detail, you found that not. More often than not, they were regularly spaced. They weren't just appearing at random, but they were recurrent at certain places in the atmosphere and lived for quite exceptionally long times, more than a couple of supergranular lifetimes. So there was something weird going on. And so, from a snapshot like the one in front of you, see if this works, you can play games and start to track them with time. And so I'm going to jump to the chase and show a progression of EUV bright point density as a function of time overlaid with the centroid and standard deviation of the histograms of the density function as a function of time and latitude. Does it look familiar? You have bands, swathes of things that start round about 55 degrees latitude and swing down to the equator over timescales of about 20 plus years. In fact, in this case, it's pretty clear that you have multiple of these bands on the disk at the same time. One of the things that we identified pretty early on was the fact that there was a very, very abrupt shift in the population density of the bright points, and you can't really appreciate it from this plot, but you'll see in another couple of plots that when these bands appeared to, they didn't slowly diffuse away at the equator. They just disappeared. And with that disappearance, we saw a dramatic growth in the number of sunspots at mid-latitudes. In the paper we wrote on this that took 3 years to get through peer review, we saw such a rapid change that we could not indistinguish it from being less than one rotation. We just didn't have the data. So, from a schematic standpoint, this is a heavily colorized cartoon, as Michael said, phenomenological concept of what's going on, showing bands of opposite magnetic polarity, which we can pull out from other data, that progress from 55 degrees latitude all the way to the equator with almost always 2 in each hemisphere. Not always 2, but almost always 2. Bear in mind 55 degrees. And so one of the things that became evident was that it looked like, and again, looked like, these magnetized systems knew about one another. Their consequential phasing, for example, when we saw between this endpoint here, or endpoint here, we saw about 2 to 3 years of extended growth at mid-latitudes before it magically started to dial down the number of sunspots that it could produce. What was going on there? Well, it's also seemed to coincide with hemispheric sunspot maximum in that hemisphere. And when you reached hemispheric sunspot maximum in that hemisphere was the time that you could trace the band starting to migrate from 55 degrees towards the equator. Again, phenomenological. But there's a lot of cross-band interaction. In fact, if you start to look at things like flares and CMEs and start to wonder about the mythology behind flare physics and look into the progression of how solar flares evolve in number as a function of time, they don't neatly stack up like the solar cycle. They have significant lags. And some of that could possibly be attributed to cross-band interactions. I'll get through this. Won't talk about our successes of predicting the last cycle, at least in timing, certainly not in amplitude. But what we discovered was that the hemispheric maxima, these times when the bands migrated from 55 degrees latitude, were almost always 21.8 years apart from the one of the same polarity that preceded it. So it seems very cyclic in nature at high latitudes. So going back to the data a little bit, the raw data, and try to explain the landmarks, I'll put on the highly symmetrized torsional oscillation plot, which, guess what, maps 1-to-1 with the progression of these small-scale magnetic features that appear to have deep roots. I'm not going to say where deep is, but they're one and the same. One of the quirks of doing this kind of analysis, and in 2011, when we started to try and explore the termination event that happened in 2011, we had the ability to map UV bright points from the 3 spacecraft stereo, the 2 stereo spacecraft plus SDO. And fortuitously, you had full coverage of the corona, so you can start to put together longitude versus latitude evolution with time, and also start to make crude polar predictions. And if you remember that I called out 55 degrees latitude earlier, you'll notice that the population density of EUV bright points goes to almost 0 above 55 degrees latitude. Hold that one in reserve, because I'm going to ask you a question. What is going on with convection or flux transport above 55 degrees latitude? Looking at these termination events, it's possibly clearer now to see, and in fact, the signal to noise in EIT is fantastic, but in SDO, it's stellar. And so here you can see, pardon the pun, you can see the dramatic drop in number of these EUV bright points at the equator, but then the consistent rise at mid-latitudes. In fact, it's about 100% modulation. So, several things have popped up in trying to get this work dealt with. People want to understand what the time frame is. We said glibly that it was about a rotation. That's not very scientific. I agree, it's not. But then if you can figure out the time scale that something that's happening at the equator can transfer information to the mid-latitudes, it's telling you something about the medium through which that information is being carried. We were accused of cherry picking because we only had one event. In fact, the cherry picking continued when we had 6 events. But anyway, what can we infer, and also what might we learn about the upcoming solar cycle, which everyone seems to be all excited about? So if I talk about the abrupt end of cycles, and I've kind of upped the contrast in these to exemplify the net change, And I start to dial in a little bit and look at the contrast between the mid-latitudes and the equatorial belts. Like I said, an EIT resolution is not fantastic, but if you take the net difference with time on this bottom trace, you see that the population density of the mid-latitudes relative to the equator increases by 100% over a very short time scale. In AIA, it's that little bit cleaner. You can see the growth of the north and southern bands and the deficit, sorry, it's green for some of those of you that are green-blue colorblind, sorry. There's a drop of 100% and then an increase of, 50 and 100. But because of the way 2011 worked out, we could pin it down to about a day in the sense of when the transition predominantly happened, triggering around February the 11th, 2011. Comparing to the stereo B measurements, again, commensurate resolution with EIT. At this distance from the sun, you can see there's a significant ramp up in the activity belts, but a ramp down. Maybe I'm hammering the point, maybe not. The one thing that's very interesting once you have these three data sets is that you can compare them, because each of the spacecraft were comparing a different longitude on the sun instantaneously. And so if you were seeing some kind of step function, how long did it take before that step function was visible at one spacecraft and then the other? And then it turned out, if you cross-correlate the signals, there was about an 8-day lag all the way around. So whatever was happening on the central meridian took about 8 days to get past stereo B, then another 8 days to get to stereo A. And then after that, they were all at a new pedestal of activity. So when you, naturally, if you then stack the data respective to those lags, everything kind of lines up, subject to evolution. So the three vantage points show the same phenomena, no shock. The change in activity seems to occur on a timescale of one rotation or less, still not terribly scientific. When you start to look at the corona, now remember what I said about the corona being like a coral. It shows changes to the underlying environment very clearly. And so this is a trace from the 335 line, I think it's iron 14, from STO Eve. And you can see that it's tonking along solar minimum at a value of about this tick mark. And suddenly after February the 11th, 2011, it hits a new plateau. And the ramp, if you look at the inset, is about 8 to 16 days. It takes to go from one ramp to the next ramp. If you're even further puzzled, you can look at how that signature varies as a function of temperature, because some of us are perverse and want to do things like that. Because I want to see how the atmosphere responds as a system to what's going on underneath it. And if I start off with helium-2, 304, and go all the way to iron 16, you can see that at helium-2, the response is small, it's a few percent. But by the time I get to 2 million degrees, it's 85%. And so if you can draw in your mind's eye the performance, the post-termination to the pre to post ratio, you see that there's an almost Gaussian response to that change in flux emergence after February 11th, 2011. You can also play games, further games, with the stereo SDO data and make Hofmüller diagrams. Favorite trick of the meteorologist. So you're making longitude versus time at fixed latitude, sampling the data set. And so here we have the equatorial band versus the northern and southern activity belts. And you can see the kind of precipitous drop in the equator, but then you see one active longitude in the north, followed by many, many more active longitudes in little more than a rotation. And if you look at the sunspot number chart at the bottom, you can see that actually there's very profound surges in the sunspot number that are directly related to this longitudinal behavior. So I always compare it to the It'll be like a prairie fire if you're from this part of the world, where it just starts in one place, then all of a sudden explodes all over the place. You have one active longitude that suddenly begets many. Something has changed. If I play games with the EVE data and start to sample it as though time was a rotational period, so I'm imposing a rotational period of 28 days on the data, and this is Lyman alpha. So again, chromospheric response. I see nothing, and after February 11th, 2011, it just jumps. Not much, 5%. And as I showed you earlier, the corona does the same thing. So there's a switch on of activity. No surprise on the ground. In 2011, F10.7 shows exactly the same phenomenon. Again, you get an order of magnitude increase in the coronal emission. For 1997, it does the same, but it's kind of ratty. Just to go back to the schematic, you see the end, or appears to be the end of cycle at the equator, rapid growth at mid-latitudes. You see the sunspot area dramatically increasing from a few millihemispheres, microhemispheres, to many hundreds of microhemispheres in a very short period of time. F10.7 goes back to 1959. You can see, maybe not on that plot, but you can see these step functions in F10.7 going back over now 5 solar cycles. Keith Strong, Julia Saba reported seeing these in the X-ray emissivity of the corona. Shock horror, they're there also, where it's orders of magnitude change you see in the X-ray corona. The magnesium-2 chromospheric index also shows these things. So when the death of one cycle at the equator is rapidly met with growth at mid-latitudes, affects all these proxies of activity by varying amounts. So some questions. Information is clearly being carried inside the system. It takes a very short time. How does it do it? What's implied here? So you can explore whether or not the convective overturn time can accommodate such a rapid transition of, or carry of information from low to mid latitudes. According to my colleagues, who I won't point out in the room, that's about the order of 100 days. So we'll do the Goldilocks method of scientific inference. It's too long. Could it be an Alphane wave that's carrying the information somewhere in the interior? 3 minutes? Really? 50 kilogauss toroidal fields? That means toroidal fields are orders of magnitude higher, probably too much. And then there's the option of a gravity wave, or some kind of buoyancy wave that's being regulated deep in the atmosphere that's modulating flux emergence. Longer time periods. Here's the one for life. You'll like this. Look at the filament distribution as a function of time, going back to 1875. Look at these streaks at high latitudes. This is now plotted as the highest latitude filament in the system. Do you notice those vertical dashed lines? Those are these termination points in cycles. They also see the launch of what has been called the rush to the poles of filaments. So not only is there a process that's going at mid-latitudes, there's another one going on at 55 degrees that is part and parcel of the polar reversal. It's synchronized. So what's going on at 55 degrees? Are these events synchronized? And you'll notice, of course, that even if these ones are synchronized, hemispheric maxima themselves are not. So there's something playing out here that we don't really quite understand. And so do you want to take the red pill or the blue pill? So you may not get that. Well, I don't even have the blue pill slides prepared, so you're okay. But that's what happens when you can do other meteorological techniques like superposed epoch analysis if you think you understand the key time of the data. And in other words, if you watch this bottom slide carefully, you can take a whole myriad of data and collapse it on itself once you've identified what these terminator times are. So since I owe it to my colleague in the room, and I'm going to finish, Jesper, Mosumi came up with this very elegant description of what she may have thought the buoyancy wave was. So it's been dubbed a tsunami because it's kind of what it's like. But if the bands near the solar equator are in close conjunction with one another, when they suddenly go, it's almost like a dam breaking. Changes the pressure balance everywhere, and somehow that pressure balance change has to be communicated across the system. And in this case, as the information travels from the equator to mid-latitudes, it basically bodily lifts the flux system at mid-latitudes. Now, this doesn't have the flux system also at high latitudes. I don't think. But you've got to worry about that one too, because there's clearly something going on at 55 degrees that's a bit of a mystery. Or not, maybe Jesper knows what it is. And so I thought that this was a kind of elegant solution. Who knows if that's really the case. But watch out, because in about 6 months, there's another one of these coming. So as the bands of cycle 24 die at the equator, and we saw them in Rachel's plots too, just watch for the growth of cycle 25, because it may yield some surprises. And that's it. Thank you.
Okay, let's see for questions. Savani wants to ask something.
Scott, when you showed your initial figures where the bright points suddenly end at the equator, I noticed that it was always after the minimum of the sunspot number. So do you have a comment on that? So, I mean, you call it the terminator. To me, it's more like that's the birth of the new cycle rather than the end of the old cycle.
It's a bit of both. Good point. But it's kind of like the both. And so if I go back, now it can take 20 minutes, right, Jesper? If I go all the way back, you'll notice, Sarvani, what is solar minimum in this picture? I have 4 interactingly oppositely signed bands around the equator. What's to say that those things are not just negating one another, or there's not enough free flux to make spots? It then requires 2 of them to die in order to beget spots on the 2 remaining ones at mid-latitudes. So in that case, solar minimum is just the time of maximum cancellation, right? So yeah, naturally the terminator would come after the bottom point of the total integrated sunspot cycle. So because what I'm trying to say is that the sunspot cycle is an interference pattern of a sort.
Any other questions? No, people are still ruminating over lunch. Okay, well, let's thank the speaker again, who's made up for starting late. And the next speaker is Aaron Birch, who will talk about local helioseismology methods and results. And yeah, 25 minutes again.
Scott? Okay, thanks, Jesper. Whoop, wrong gives me. Nope. Okay. Yeah, is that one going here somehow? Oh, it's in no. You have to borrow Sasha's dongle. Okay, Sasha here. But for a Sasha, what was the one you had this morning? Yeah. Yeah, that would. That one grab that. Grab that one. That one worked. Yeah, yeah. This is good. All right. To-do list.
So everybody else, use the break, check that your computer plugs in. Good idea.
Okay, all right. So I'm going to talk about local helioseismology. Local helioseismology is the use of solar oscillations to probe the interior in 3 dimensions. And we can do the surface too. There are a bunch of different methods of local helioseismology, but I think an important thing to keep in mind is that the underlying idea in these methods is really all the same. It's about measuring correlations in the wave field and interpreting these correlations. And the correlations have information beyond just what's encoded in the normal mode frequencies. I wanted to show a little bit about the input data. I think no one has showed a Dopplergram yet. Here's a Dopplergram. So it's telling us about the line of sight component of motion. The large scale gradient across the image is rotation. And these small modeled features are the supergranulation. If you play a movie, you see this little flickering stuff. That's the P modes. It doesn't look that impressive in this movie, but they look great in a power spectrum. So here's the horizontal scale. This is angular degree L. You can read the horizontal scale in megameters at the top. This is frequency. Red means you have a lot of power. These ridges are the P modes. This is the F mode, the deep water wave, and you have convection at low frequency. And local helioseismology is all about interpreting these observations of waves. This is a figure from 2010, and I think it holds up pretty well. You have sources of observations here, SOHO, MDI, GONG, this is the ground-based telescope network, and HMI. And then there's this list of methods that take advantage of these sources of data. And they all today have the same names they used to, except for direct modeling, which is slowly being rebranded as mode coupling. And Siobhan will talk about that later today, so I won't get into it. And there's this list of science topics. And here they're organized in order of spatial scale. At the smallest scale, supergranulation, things like interior atmosphere coupling, and then going up through global scale dynamics. And yeah, as we go through, we'll talk about a bunch of these topics. The first method I wanted to talk about is time-distance helioseismology. This was introduced by Tom Duval in '93. And the central calculation in time distance is this cross covariance. Phi is your observable, so you can think here the Doppler velocity, but it doesn't have to be, it could be intensity. X1 and X2 are 2 locations on the surface, and T is this time lag. And if you just compute the cross covariance and look at it, and well, you have to do a lot of averaging, you get a nice figure like this. The horizontal axis is the angular separation between X1 and X2. And the y-axis is the time lag. And you see these little ripples in the cross covariance. These are telling you about waves that you see at X1 at some time, and then sometime later you see them at X2. And where they show up on this diagram tells you about the wave travel time. And here are some ray paths and their corresponding positions on the time distance diagram. So here's 1 and 1 prime, for example, 1 and 1 prime. These are the single skip arrivals. And you have some more complicated things like this 3 prime that's used in far side imaging. Okay, so that's the first part. Compute the cross covariance, just a mechanical operation. And the insight then is that the changes in the cross covariance are telling you about internal structure and flows. So imagine this simple experiment. You have two observation locations, x1 and x2, and imagine you have a uniform flow in between them. Blue is the cross covariance with no flow. Red is the cross covariance with a very strong flow, kilometer per second. And this is just for a case of surface waves, F modes, to keep it simple. And the waves that are going downstream, so these are the guys with positive time lag, you see that this flow moves the cross covariance function to shorter time lags. The waves are going faster. And the other half of the cross correlation is for waves going in the opposite direction. These guys are going upstream. And this is it. You measure a cross covariance, and the shape of this cross covariance tells you about what's happening in the interior. I wanted to also mention holography. This is a more complicated version of time distance, but it's conceptually very similar. It's about interpreting these cross covariances. Something like an ingression-egression correlation in the terminology of holography. If you write it on a piece of paper, it's formally equivalent to averaging a bunch of time distance cross correlations, but just shifting them in time and changing their amplitudes. And a special case of this is far-side imaging, and there's a poster about that. So check it out. Okay. I wanted to also say a little bit about ring diagram helioseismology. And this is the way I think about it, an extension of some of the ideas of global mode helioseismology. It's about measuring the dispersion relation, only here we're measuring the local dispersion relation instead of the global dispersion relation. And the procedure is relatively simple. You select some patch of the sun and you track it as it rotates across the disk. This gives you a data cube, so Doppler velocity as a function of x, y, and t, where x and y are your two horizontal positions. And you can compute the Fourier transform and the power spectrum of this thing. And here's an example. Here's a cut in the kx, ky plane. So kx, ky, this is the horizontal wave vector. You take a cut at constant frequency, and you see these rings. Again, red means high power. The F mode is the outermost ring, then you have the P1 and so on. And the position of the rings is telling you about the local flow. You can think about this flow U just producing a Doppler shift in your power spectrum. You can also see this effect if you take cuts instead of at constant frequency, you take a cut at constant wave number. So you're unwrapping your 3D power spectrum at constant wave number. And you see the sinusoidal variation of the ridge frequency with the azimuth of the wave vector. And so one way to fit is you fit for these sinusoidal variations. And those fit parameters tell you about the flows. Okay. So this is what we've talked about so far is making measurements. But that's really only half the problem. The other problem is, well, okay, how do you go from some set of measurements to saying something about physical conditions in the sun? And the first step is this forward problem. So given some model for physical conditions in the interior, what do you predict for your measurements? And then the inverse problem is, well, the inverse. Given helioseismic measurements, how can you say something about what's happening in the interior? Here's the one slide summary of the history of forward problem for local helioseismology. Started with the ray approximation. This is geometric optics. So you have a phase of your wave packet that just accumulates along a ray path. And this is good for perturbations that are smooth and weak. Then came the Born approximation. So here's an example Born approximation calculation. It's telling you about the sensitivity of travel times between these 2 points. This is a single scattering approximation, and it lets you drop this assumption that the perturbations are smooth, but they still have to be weak. And if you want to go past that, then you're into the numerical wave propagation, which is nice because it's extremely general. You don't have this constraint of smoothness. You don't have the constraint that the perturbations are weak. Another advantage is that it lets you include a lot of effects that are very difficult to put into the semi-analytical approximations. So something like the foreshortening is relatively straightforward to put into the numerical wave propagation, but pretty painful to do in the Born approximation. Yeah. Okay, inverse problems. The first thing to say is that essentially all inverse problems that are done in local helioseismology are linear inverse problems, which means you need to somehow linearize your forward problem. For the ray approximation and the Born approximation, that's okay. It's done for you, basically. And a thing to keep in mind is that these linear inversions are basically always very sensitive to noise. They're ill-conditioned linear systems that you have to solve. So you have to do something to get rid of this sensitivity to the noise. And this is a big part of the art of inversions, is what extra assumptions can you make that are good for the problem you're trying to do to get rid of this sensitivity to noise. And I wanted to get into the guts of it a little bit, to say a little bit more about Michael's contribution to this topic. And I think also, as Rachel said earlier, it's hard to talk about Michael's contributions without showing some equations. So we're going to do it. So imagine we have our measured data points, whatever they are, these DI. Think of them as travel times or ring fit parameters or whatever other measurement you've made with your local helioseismology method. You have some kernels. People have mentioned them a few times before. These are functions that tell you how you think your measurements should depend on perturbations to your reference model. And you have your delta Q, and these are the unknown perturbations to the reference model. These are the things you want to find. So these are things like, what are the flows in the interior? And these things are all connected by a set of equations like this. For each measurement I, you have a kernel I that depends on the kind of perturbation. So you could imagine, Sarbani showed the special case where you had changes in sound speed and density, I think. Yeah, and then of course there's noise. I really enjoyed reading this review. It's a very clear discussion, and it uses the example of 1D rotation inversions, but the ideas that it describes are really very general. Okay, so how are we going to solve that system? In the RLS method, the idea is you want to find a model that gives you the best fit between the predictions of your model and your observations. And if you just try to implement that by itself, what you find is always just nonsense because of the sensitivity to noise that I was talking about. And so you need some way to control your solutions. And the way you do that is, instead of minimizing, the difference between the predictions and the data, you add some extra term or terms that control some properties of the solution that you don't like. So maybe you say, I want smooth solutions. And a few people have mentioned OLA methods already. And I wanted to show that in a little more detail. And the key insight here is that we're doing a linear inversion. So it means that our inferred properties are going to be some linear combinations of the input data. And that's all this is. It says that the inferred perturbation at some point x0 is some linear combination, so with these weights ci of the data, di. But we know how these guys, the di, are connected to the delta q. That's what the kernels tell us. So we can insert that expression in here, and you just reorganize a little bit, and you find that your inversion result is some weighted average of the true perturbations, assuming that your kernel functions are correct. And of course, there's a plus noise bit on here. And these curly k's are the averaging kernels, and they're just this weighted sum of the sensitivity kernels. And the idea of OLA methods is to say, well, let's make nice averaging kernels. This paper was mentioned already. Bill, you talked about it, yeah. And here, Frank and Michael proposed this thing called SOLA, so subtractive OLA. And here, the inversion is based on two things. One is there's this term that says, give me an averaging kernel that's close to my target. And this target you have to pick based on the problem that you're doing and knowing something about the physics. And then there's this penalty term, this EI is the error covariance. And so this is controlling the error bar on your inversion result. So you minimize this thing, and it leads to this linear system. And the thing that's interesting here is that the matrix you have to invert is this thing, integral of k times k. And that matrix doesn't depend on the target function. And it means you can solve efficiently for many target functions. You only need to invert this matrix once, and then you're good to go. And this is different. There were previous versions of OLA where instead of this square of a difference, you had a weight function times a kernel. And you were trying to opt to minimize that. The weight function was something that would penalize having a kernel that was too spread out. And the drawback of that is then you end up with this weight function sitting underneath this integral. And it means every time you change your weight function, you have to reinvert your matrix. So this was a really nice idea. And as people have talked about, it's been used in a lot of global mode applications. But I wanted to highlight one paper where it was used for local helioseismology. And that's this one. And it was a paper about inverting F-mode travel times. So these are the surface gravity waves. Inverting F-mode travel times to learn about horizontal flows near the surface. And in this paper, we used the Solar method. And it was later generalized to include modes from other radial orders, but the idea is the same. And I think this is a nice example of something that Michael did in one context that proved to be very useful in another. And I wanted to show a result just because mostly because the figure is beautiful. I really like this one. These are horizontal flows inferred from local helioseismology around a sunspot. The background colors are the magnetogram. It's pretty saturated. Here's your spot. Here's the mote flow. Here's a supergranule. It's cleared almost all of the magnetic field out. You see part of a supergranule here. You see a little one here. Another one there. I like the figure a lot. Okay. And then I also wanted to show some recent results. So a natural slide would be results about meridional flow, but Paul Rajaguru is talking just after me, and so I leave that topic for him. I think it's a wonderful topic. I wanted to say a little bit about convection, but it's going to be very brief. And I just wanted to point you to some posters. And Shravan is this afternoon, and Mark Rast tomorrow morning, right? Yeah. Maybe you guys have seen some versions of this figure before, but I wanted to show it again. So there are a lot of different estimates of subsurface convection, the strength of subsurface convection. So this x-axis is angular degree again, so it's telling you about the horizontal scale. Large scale is over here, small scale is over here. And here's the RMS V phi, so the RMS east-west velocity per multiplet in the convection. This black curve is a revised version of the result from Hanasoge and Duval. This is a time distance upper limit on the strength of convection at this depth, 0.96. This blue curve is a revised version of what was published in this ring diagram paper. This is a really interesting paper. Most ring diagram inversions are 1D inversions. And in this paper, they were using 3D inversions of very highly overlapped tiles to get, to improve the horizontal resolution of the method. And I think that's a really cool idea. Red is correlation tracking, and gray is the east-west velocity from an ASH simulation from one of the MICHE 2008. And the reason for these revisions, I don't have time to get into the details of them, is to basically fix some apples and oranges comparisons that have been floating around in the literature. The idea is, the basic result has not changed. It's that this estimate from Greer is well above the upper limit from time distance. And this estimate from time distance is well below what happened in that one particular ASH simulation. And so we're trying to get this all sorted out, but that's the current state. I also wanted to say a little bit about Rossby waves. There are 3 posters that I counted about Rossby waves. If I missed one, I'm sorry. So if you look in, say, this paper from SIO, it shows some eigenfunctions for Rossby waves in uniformly rotating stars. This left panel shows the north-south velocity. This is the east-west velocity, and this is the radial vorticity. This is for some particular L and M. So in particular, these are sectoral modes. L equals M equals 5. And the first unambiguous detection of these textbook Rossby waves was done by Luptian 2018, and it was done using surface flows measured using granulation tracking. And in this paper, Zhixiao Liang confirmed this detection using time-distance helioseismology. And the method was inspired by this picture here that says, hey, a good way to measure these equatorial Rossby waves is to measure north-south velocities. So that's what he did. The ray geometry is here. So this is a meridional plane. And the measurements are just like the measurements that have been used traditionally for measuring the meridional flow. They're just these north-south travel time differences that are sensitive to north-south flows. The detection has also been confirmed using mode coupling. Maybe Shravan will talk about that, and ring diagrams. Oh, and here's the power spectrum. So these are power spectra of these travel times. The x-axis is the azimuthal order. This is the frequency. Black means large power, and you see this little ridge here. Blue is the theoretical expectation. And these are just copies from the window function. The last result I wanted to show is about flows around active regions. It's been known for a while that there are flows with horizontal scales of 10 degrees or so around active regions. These flows may be important for flux transport, and there are a lot of open questions about them. And Jesper's standing up. But I'll still say a little bit. The question is, what is the underlying physics? There's this idea from Sprout that these are inflows driven by cooling in the active region. How do they form and evolve? What do these things depend on? In particular, if you think cooling is the driver, then maybe the ratio of spot to plage is important. And then to show the result. So this is from a Brown 2019 paper that looked at 336 active regions, measured horizontal flows for each of these things, and then stacked them up. And the active regions were divided into groups by flux. The background color is the magnetic field. These are for the weakest regions. You see an inflow. These are slightly stronger regions. You're still seeing an inflow. It looks like it's more into the trailing polarity than the leading. And it's a little hard to see, but there's this retrograde flow sitting on the poleward side. And as far as I know, that hasn't really been seen clearly before. Okay, this is my last slide. So my summary here, we have great data sets, MDI, GONG, HMI. I think there are a lot of important physics problems that are still to be addressed. I didn't have time to talk about it, but the question of what sustains the differential rotation and the meridional flow. My opinion is that we don't have a convincing answer yet to the question of where active regions come from. I would like to know the answer to that. Also, the question, is the mixing length picture of convection basically correct? And I guess Mark will get into it tomorrow morning. The methods are largely established, but there are a lot of opportunities for optimization still. For an example, check out Kaori's poster, it's number 12, about ring diagrams. And of course, there are still issues. We have to take care of the center to limb effect. And that's what I wanted to say. Thank you.
Well, I guess we have time for a question or two, if they are quick. Nobody's got a question? Jan has a question.
Thank you. I want to go back to the subsurface velocity and the discrepancy between the models.
Yes.
And those models would actually agree pretty well with mixing length theory, I think, to order of magnitude, if you calculate convective velocity there.
Yes.
And then you have the black curve, which is terrible. But then you also have the blue curve. And so the real question is, what's the reason for the discrepancy between blue and black? Never mind the models, they're wrong, but
yeah.
there are two observations showing different things.
Yes. Short answer, I don't know. Longer answer, we're working on it. We've been grinding through that. There's a poster by Kaori where we found some issues with the fitting code that was used there, and we did Monte Carlo tests of the improved code, and it looks pretty good. But the issues we found were not big enough to explain this. So we'll keep going.
Thank you. Keep us posted.
Okay, Charles, very quick question, and then we'll go to the next speaker.
This is the black curve. Oops, sorry.
Sorry, the question I had was, are those detections or upper limits?
Yeah. The black curve is an upper limit. The blue curve is a detection. The red curve is a detection. And the gray is from a simulation. Yeah.
Okay, well, let's thank Jan again. And the next speaker is Paul Vadiguro, who's going to tell us about local seismology of deep meridional circulation.
This wasn't yours, right? This
No.
was-
So I have it in this.
Give me just a second. There you go. Looks like it turned up.
I don't know. Should be on. It's not mine.
Hmm?
It's not my laptop. It is. Yeah. Oh,
It was there for a second.
okay.
Right, yeah.
All right.
So this advances. And this is the laser plan.
Okay. Okay. So I first learned time distance helioseismology as a postdoc of Mike Thompson at Imperial College under his mentorship. That was mostly in the context of local helioseismology. But what I learned under him, we have been using it recently to study the meridional flow. And that's what I'm going to talk about. Even though my title is kind of general, but I'll be focusing on some latest aspects, some latest analysis which we have been doing with contributions from these people. So even though all of these names are here, what I will talk about may not necessarily be the viewpoints of all those people here. Okay. So we heard a lot about meridional circulations. You all know what it is. It's a complex, sun is a very complex fluid dynamical system. So much of the activity, the solar dynamo, all the activity which we see is thought to be driven by these large scale flows in the interior, the differential rotation, and the meridional circulation. At least some of the dynamo models, the most successful dynamo models, do depend on meridional circulation for their working. So I just summarized this results, what we know so far from the published results on deep structure of meridional circulation. Here I have just compared the 3 results which have been published. All are ray theory inversions. And this is for the first one which appeared in 2013 by Junwei. And the color scales are different. The colors are different in different panels because I just cut from the papers, so the color schemes are different. For example, here what is plotted is southward speed. These two are northward speed. But anyway, so as you can easily see, these first 2 panels show you kind of a very shallow return flow here, and this result of Junwei shows a second cell which is stacked in depth, a double cell structure. And what we did in 2015, myself and NCAR, we did not find this double cell. And what we see here is a single cell. But there are hints of some multiple cells at the very low latitudes. And these are some more results which appeared recently. And this is from Ruizu and Junwei again. And they again seem to confirm that there is a double cell. And Lin and Chow, for some reason which I don't understand, they did only inversion for the very low latitudes. And they find a double cell at the low latitudes. And more recently, a student of Shravan is here. They did develop bond kernels for meridional flow measurements, and they applied that on our data, and we can get the same single cell results. Okay, so the one difference between the measurements which are shown here is that our results, we use the stream function for the extracting the meridional flow, so it automatically satisfies the mass conservation. Okay, it's a close comparison of what we have. since we use the stream function, we could recover the radial component of the flow too. So this is the radial component and this is the meridional component. So this is with mass conservation and this is without mass conservation. One obvious difference which you can see is that once you apply this mass conservation, there are much smoother structures, solutions, which is expected. And also the magnitude of the flows goes down as you expect as you go to deeper and deeper layers. But that is not the case in these measurements. Okay, so what I'm going to address mostly is that what is the origin of these differences? Okay, so this is just a cut across what I showed from my results from here. So very consistently we see the flow profile changes sign at about 0.77, and the hint of some sign change here you do see at the low latitudes. These are the different curves are for different latitudes, and there is a signature of some sign change, but within our error bars they are not significant. So so we concluded that the overall meridional circulation return flow is somewhere below here. Okay, so what is the difference due to? That's what I'm going to address the rest of my talk. So there can be two possible reasons. One, the travel times which you measure in different methods have different information, and so the travel times could be the cause, or the inversions, the input physics. For example, we use mass conservation, but the others did not use. So we did. When you talk about travel times, one of the important things to worry about is what Junwei discovered in 2012. That is called center to limb systematics, and there is a systematic travel time which you measure. For example, here it is the travel times on the surface plotted the 2D representation of the travel times. This is for the north-south measurements. You align the arcs in the north-south direction. You measure the travel time differences, which will tell you the flow in the north-south direction. And when he did it in the east-west, he found this systematic. And this is obviously a systematic because you don't have a flow on the sun across the hemispheres and vertically. So that since this is a systematics, there are more detailed analysis of that which kind of confirmed, that's what Junwei discovered, which confirmed that is a systematic. So the technique was to rotate this and subtract it from the north-south measurements and then do the inversions. That's the strategy which Junwei applied, and it successfully worked. For example, in the near surface measurements, if you don't remove the systematics, you get this dotted curves, and after you remove the systematics, and it agrees with other surface measurements. Okay, so now we had a team formed at EC Bern to analyze more closely what is going on. So one of the proposal was to look at the travel times, the device strategies to differentiate systematics and the signals. So one of the things was to analyze the frequency dependence of the travel times, and that is what we found. And so these are the systematics. As you can see, there is a very strong frequency dependence in the systematics. Here is a cut across as a travel distance, and then the different frequency bands which you use. So when I say frequencies, we filter the cross correlation. After you measure the cross correlation, you filter the cross correlation over different frequency bands, and then you measure the travel times. So at these different frequencies with a width of 1 millihertz in your filter. So this is for a plot of the travel time, the systematics, center to limb systematics, as a function of travel distance and the frequency. As you can see, there is a very large frequency dependence. The signal peaks. These are at different latitude ranges, and the signal peaks, the systematic peaks at about 4 millihertz. So it's a very strong frequency dependence. So then we did this exercise of measuring the systematics at each frequency bands and then subtracted from the north-south measurements. And this is one example of how it looks like. This is the systematics, and then after you remove the systematics, and this is the travel times as a function of frequency and distances. But obviously, if you closely see this, where the systematics is large, you see kind of correspondence with the travel time signals which you get. So this is as a function of frequency, and there seems to be a since the systematics peaks around 4 millihertz, right around 4 millihertz, you see this travel times turning cyan into blue, whereas those lower frequencies do not change. So this kind of may indicate that there is, so that means that if you make even a slightest mistake in measuring the systematics, then it will leak into, it will have a signature in your signals for meridional flow. So okay, not surprisingly, when we did the inversion for different frequencies, this is what we find. So at the lower frequencies, we get a single cell. So these are the meridional component and the radial component. At 2.7 and 3 millihertz, you see a single cell, but when you do it at 4 and 4.5 millihertz, you obviously see this double cell, just like what Junwai's original publication was. And so that is a kind of intriguing result. Now, so the sun should not show you a different phase and different frequencies, because there is only one flow inside the sun, but you get different results if you use different frequency bands. So this kind of indicates that there is something wrong with your measurement of systematics. That is one aspect. And when you do the joint inversion of all frequencies travel times, and you again get a kind of a shallow return flow and looks like a double cell, whereas the inversion of unfiltered travel times gives you a single cell. This is the older result. So that is what we have so far. So the summary so far is the strong frequency dependence of Sentinel limb systematics makes the measurements of deep meridional circulation highly sensitive to how the CLS is measured and removed. Okay, what else? So that I did since we have about 7 years of data now, I mean, we have actually 9 years of data. I used, the first 7 years. And these different frequency measurements, I studied the temporal variation at these different frequencies. So this is 3 millihertz and 4.5 millihertz. And this is actually the average magnetic field. So these are the changes in meridional flow. You take the mean of all the years and subtract it from each month here. It's a one year running average. That's what we use for the measurements. Use a travel time of 1 year running average and do the inversion every month. And these are the residuals, the temporal variation of meridional flow, so to speak. And you see the familiar structure of, actually the red and blue are the flows around active regions. There is a inflow towards active region. So this is the inflow, and this is the flow towards the active region, and this is again from the north to south. Here is south to the north, and this is the active region belt. And this is somewhat similar to the zonal flow structure which you see. And the purpose of showing these figures are to show that at different depths close to the surface, the different frequencies results do agree, as you can see here, these structures. But there are some finer structures at higher frequency as you expect, but then overall the temporal variation agrees in the near surface at the different frequency bands. So that, again, I use this to conclude that this is again a comparison of, so the structures you see in the temporal variation for the near surface at the different frequencies, they all agree. So the difference due to the difference in the different frequency bands for the deeper flow is then mainly due to the way you remove systematic. That is my current conclusion, but it's not yet published. But there are different groups working on it now. I'm sure they may have different conclusions on what they see, but this is my conclusion. I think I'll stop it here.
Okay, questions? Yep.
Thank you, Paul. did you check the cross covariance in your measurements? You might remember we did this cross covariance checks at the EC meetings, and where we could explain most of the discrepancies between all the methods being not right modeled covariance matrices.
I haven't compared the travel times from the other people, but yeah, is that what I mean? I haven't compared with the.
It would be interesting if you would have that for all these different frequency bands to have the full covariance matrix.
Oh, okay.
Yeah.
Yeah.
I assume you did just the diagonal covariance matrix.
Yeah.
Yeah.
Okay. All right. Okay, we should do that. Yeah, we haven't done that.
Any other questions? Yes.
Can you comment on the variation of the noise with frequency and whether all these variations are actually significant?
Oh, I don't have a figure, but I don't remember seeing any particular trend in the noise as a function of frequency, but I think slightly larger noise at the larger frequencies, which, you know, the power is little less as you go away from the 3 millihertz peak. So the less the power, I think the larger is the noise in the oscillation which you use. But I haven't plotted the noise as a function of frequency yet, but only the systematics I have been checking. But yeah, but then the effect of systematics seems to be much larger than the noise. That's my first impression, but I haven't not done the full analysis yet.
Okay, and Jan has a question.
Thank you. Do you understand the reason for the center to limb effect? I mean, naively, that would be a simple geometry, but it clearly isn't.
Yeah, so we haven't fully understood. I think there are some papers which what we call as C. Charles Ballner and what is that? Okay, BS effect. Yeah, BS effect, which kind of attributes that to the effect of convection on the oscillations. Is it mostly due to the upflow of the convection, which kind of systematically shifts the frequencies and the travel times in a particular way? They have a model, successful model, but then I'm not sure if they have able to explain all of the observations which have been produced in Junwei's paper.
The model doesn't fit. I mean, it's qualitative. It's a qualitatively gives the results. We are working on the issue.
Yeah, but that's one thing which we have to figure out, because once you understand, when you have a good model of what it is, where it is coming from, then you will be sure that you are removing something which is really systematic or whatever it is. Yeah.
Yes, Kosenik has a comment down there. Does he want to make it public? Okay, good. Okay, excellent. Any other questions? I guess not. Well, in that case, we'll thank Paul again. And the next session is at 3:30. Remember that you can sign the papers outside with any thoughts you might have on Mike. And also remember to look at the posters. And I'll see you in 40 minutes.